Hello everyone. Today, I, Abhishek Jha, am going to present the paper titled Comparative Analysis of SOI Bulk Rectangular and Nanowire Optical Waveguide for Label-Free Lung Cancer Detection. This paper was written by me, Abhishek Jha, and my batchmate, Abhishek Kumar, under the guidance of our professor, Dr. Rituraj Singh. Now here is the content slide, which is basically a summary of everything that I'm going to present today. Now moving on to our topic, let me introduce you to lung cancer and its various characteristics. Well, lung cancer is a malignant lung tumor characterized by uncontrolled cell growth in tissues of the lungs. This growth can spread beyond the lung and into nearby tissues or other parts of the body by the process of metastasis. Let us further know what are the factors causing lung cancer. Smoking, secondhand smoking, family history, harmful infection, and air pollution are some of the major contributors to lung cancer. This list is not exhaustive, and there can be many other factors, but these are some of the major ones. The symptoms of lung cancer include facial or neck swelling, chest pain, coughing of blood, weight loss, loss of appetite, and trouble breathing. There can be other symptoms as well, and again, this list is not exhaustive. Broadly, there are two types of lung cancer. They are non-small cell lung cancer, that is NSCLC, and small cell lung cancer, that is SCLC. Let us know a bit about non-small cell lung cancer, that is NSCLC. About 80 to 85% of lung cancers are NSCLC. NSCLC consists of different types of lung cancers which start from different types of lung cells. They are grouped together because the treatment and prognosis are often similar. The main subtypes of NSCLC are adenocarcinoma, squamous cell carcinoma, and large cell carcinoma. And here I have written a bit about each of these subtypes, giving us an overview of all of them. Now, moving on to small cell lung cancer, that is SCLC. About 10% to 15% of all lung cancers are SCLC. It is also known as oat cell lung cancer. This type of lung cancer tends to grow and spread faster than NSCLC. About 70% of people with SCLC will have lung cancer that has already spread at the time they are diagnosed. Since this cancer grows quickly, it tends to respond well to chemotherapy and radiation therapy. Unfortunately, for most people, the cancer will return at some point. Talking about the various stages of lung cancer. In the first stage, the cancer is located only in the lungs and has not spread to lymph nodes. In second stage, the cancer is in the lung and nearby lymph nodes. During the third stage, which gets counted as one of the advanced stages, the cancer is found in the lung and in the lymph nodes in the middle of the chest. And during fourth and final stage, the NSCLC has spread to other lungs, the fluid around the lungs, heart, or to distant lymph nodes or organs. Now, since we have some idea about what the disease is and its various types and symptoms, let me tell you something about our research. Over the last few years, there has been a steady rise in the use of optical biosensors for diagnosis of various diseases through detection of target biomolecules. And this is what we are going to do as well. So first of all, what is an optical biosensor? An optical biosensor is a compact analytical device containing a biorecognition sensing element integrated with an optical transducer system. The basic objective of an optical biosensor is to produce a signal which is proportionate to the concentration of a measured substance, that is, analyte. And in our case, the analyte will be the lung cancer cells. There are broadly two types of biosensors. They are label-based biosensors and label-free biosensors. Label-based biosensors make use of labels like radioactive molecules, enzymes, fluorescent molecules, etc., that combine to the target analyte. Thus, the number of target molecules in the tested sample is found by measuring the label count and arriving at the corresponding value. This is usually done when the targeted analytes are hard to detect on the basis of their intrinsic physical properties. However, its major drawbacks are that the process is usually more costly, time-consuming, and labeling the biomolecules can alter the binding properties of the analyte. Coming to label-free biosensors, label-free biosensors do not use labels to measure the presence of biomolecules and instead rely directly on the intrinsic physical properties of analytes for detection. Apart from being giving real-time results, label-free biosensors has the added advantage of being cost-effective, and due to these advantages, we are also using label-free biosensors. Here is an overview of the previous work done and what we are going to do. It is an overview in a very crisp and nutshell manner. First of all, a refractive index-based passive sensing technique where the waveguide is designed using a SiO2 substrate and Si nanowires with aqueous solution as the cladding is used by the biosensor. The biosensor basically works by measuring the variation in the effective refractive index with variation in the width of the functionalization layer, which occurs when it thickens due to binding between the functionalization layer and the corresponding biomarker for the lung cancer in human serum. Here, the existing work on silicon nanowire waveguide-based label-free sensing of lung cancer is compared with well-known bulk rectangular optical waveguide. For illustrative purposes, the material and effective physical parameters used for both the waveguides are kept same. It is determined that whether a rectangular bulk waveguide and a nanowire waveguide are suitable devices for detecting the presence of target biomolecules. At 1550 nanometers, the finite element-based FOMSOL package is used to investigate the mode field profile and the effective refractive index of propagating wave. The effects of change in the functionalization layer covering are studied for the nanowire waveguide. Mainly the change in confinement factor and mode effective refractive index with respect to change in functionalization layer coverage is studied. Coming to design configuration of our waveguide, here you can see on the left-hand side, there's a bulk silicon rectangular waveguide, and on the right-hand side, there is a silicon nanowire optical rectangular waveguide. You will notice that in both the cases, we have kept almost all the dimensions same for analogous things so that the comparison becomes easy. In both cases, the waveguide consists of silicon, SiO2 substrate, and an aqueous solution. The height of the silicon rod is 220 nanometers, width of a waveguide is 750 nanometers, and the height and width of the substrate are 500 nanometers and 1255 nanometers respectively. These diagrams present the overall design of our waveguides without the functionalization layer, and this part of the experiment has been done without a functionalization layer to get an idea of the basic characteristics of the two waveguides so that we can compare them with their counterparts having functionalization layer. Before proceeding forward, let us discuss a bit about the various modes of propagation. The first one here is transverse electric mode. In this mode, the electric field is purely transverse to the direction of propagation, whereas the magnetic field is not. Thus, Ez equals to 0 and Hz is not equal to 0. Here, in all cases, Z has been considered the direction of propagation, as is the convention. Next comes transverse magnetic mode. In this mode, the magnetic field is purely transverse to the direction of propagation, where the electric field is not. That is, Ez is not equal to 0 and Hz equals to 0. In transverse electromagnetic wave, Both the electric and magnetic field are purely transverse to the direction of propagation. There are no components in z direction. Thus, Ez equals to 0 and Hz equals to 0. And in the case of hybrid modes, neither the electric nor the magnetic field is purely transverse to the direction of propagation. Hence, neither Ez equals to 0 nor Hz equals to 0. So, since we have recapitulated what modes of propagation are, let us move on to more investigation. First, talking about bulk rectangular waveguide. Here, the field components of the waveguide along each of the directions for both electric and magnetic field are given. In the first row, you can see that the electric field has high intensity value inside the waveguide in the desired region along the x direction. But unfortunately, that is not the case for both y direction and z direction. In both cases, the high intensity is not inside the waveguide and definitely not in the desired region. In case of the magnetic field, along the y direction, there is high intensity at the center of the waveguide. Which is also the desired region. But that is not the case for Hz and Hx. From this, we can conclude that the mode of propagation is quasi-TE. Moreover, by taking out the product of Ex and Hy, we can find the mode field intensity distribution of a bulk rectangular waveguide, which has been displayed on the left-hand side of the screen. Here you will see that the intensity is high at the center of the waveguide, which also happens to be the desired region. Now, moving on to silicon nanowire rectangular optical waveguide, that is SNROW. A similar modal analysis has been done here. And in the first row, for the fields, you can see that in the x direction, the electric field has high intensity value in the regions between the silicon nanowires. From this, we can conclude that the mode is quasi-TE mode. The image on the left shows regions of high intensity between the silicon nanowires and regions of low intensity inside the silicon nanowires and everywhere else. This region of high intensity between the silicon nanowires indicates that the power is flowing through between the gaps, which is something characteristic of a slot waveguide, which it sort of looks like. Upon taking out the pointer vector distribution versus the x-cut coordinate, we see that the graph has been obtained whose envelope is a Gaussian curve. Unlike a Gaussian curve, it is not smooth. There are bars and valleys that represent regions of highs and lows for the Poynting vector value. These bars are there because boundary changes. We see here that the boundary changes multiple times, and thus the physical properties like refractive index also change, like upon going from silicon wire to the aqueous solution and then from aqueous solution to the silicon wire. Thus, each of the bars here represent the areas of high intensity. That is, these bars represent the region between the silicon nanowires, and these valleys indicate regions of silicon nanowires where the intensity is low. So here also the graph keeps on rising and the bars keep on becoming taller up till the center. As is logical because the highest intensity even inside the waveguide is at the center. But since the envelope is Gaussian, we can say that overall it behaves like a rectangular waveguide. Now moving on to sensing analysis. So in our previous experiments, we had not added the functionalization layer. Now we will add the functionalization layer around both the bulk rectangular and the silicon nanowires, and the thickness of the functionalization layer will be 8 nanometers all around. You can clearly see the same in the diagram in front of you. Let us talk about comparisons. We did similar experiments on both waveguides with functionalization layer and compared them with each other and waveguides without the functionalization layer. And these comparisons gave us some significant insights. Let us look into them. First, comparison between mode field distribution of a bulk rectangular waveguide with functionalization layer and without functionalization layer. Here you can see that the distribution is almost the same. In fact, both are Gaussian-shaped curves which overlap. This shows us that even after adding a functionalization layer, there is no change in the working of a bulk rectangular waveguide, and thus, unfortunately, we cannot use bulk rectangular waveguide for detection of lung cancer cells. In the second one, comparison between mode field distribution of SNORW with functionalization layer and without functionalization layer. Well, this one is a lot more interesting than the last one because this comparison gives us some of the biggest insights of our experiment. Here, the red dotted line shows the usual graph we had seen earlier for the one without the functionalization layer. But it is interesting to note that for SNORW with functionalization layer, there are more subbars. That is, there are more peaks than the one without the functionalization layer. Here, we observe that the pointing vector rises twice instead of one, as was the case earlier. This pattern emerges in SNORW with functionalization layer because there is change in boundaries 4 times. That is, after the addition of functionalization layer, the boundary changes along the x direction upon going from functionalization layer from silicon nanowires, then from the functionalization layer to aqueous solution, then from aqueous solution again to the functionalization layer, and again from functionalization layer to the silicon nanowires. As one knows that with a change in material, there's a change in the refractive index, and thus the distribution of energy also changes. And hence we can see a small bar upon each of the larger bars. But overall, you'll see that SNORW graph with the functionalization layer is sort of like one without the functionalization layer, in the sense that even this one has bars which are regions of high energy and also has a Gaussian shaped envelope, which indicates that overall it lets wave propagate like a rectangular waveguide. These small bars also indicate that energy gets trapped inside the functionalization. Now moving on to our third comparison, which is comparison between mode field distribution of a bulk rectangular waveguide with functionalization layer and SNORW with functionalization layer. Well, here one can see that this is a very basic comparison. It can be observed that both of them have the same Gaussian shaped curve. And another insight is that the red graph is a smooth one, which is not the case for blue graph. Moreover, for the blue one, the energy is above the red graph at some places. And in some regions, the energy is below it. Thus, we can see that upon forming a slot waveguide kind of thing, in case of SNORW, what happens is that energy, which should have been in the silicon nanowire, gets transferred to regions between the silicon nanowires, and there are energy spikes. Coming to comparative discussions, the graph here is the conclusion of the second part of our experiment, where we wanted to see that whether there is any effect of functionalization layer coverage on working of a silicon nanowire waveguide. For this, we thought of seeing how the confinement factor and end effective changes with change in functionalization layer coverage. So initially, the functionalization layer coverage was taken as 12 nanometers, and it was eventually increased stepwise to 228 nanometers, and the containment factor was particularly studied. Before we jump into interpreting this graph, let us see what confinement factor is. Well, confinement factor is the ratio of power flowing through the desired region to the power flowing through the entire region. So for taking out the confinement factor, here we look into We took the area between the silicon nanowires as our desired region in the numerator part and the area of the waveguide as the denominator part. From this ratio, we obtain the confinement factor. We observe that with increase in effective personalization layer coverage, the confinement factor decreases. But what does this mean? It means that as the functionalization layer coverage was increased for the silicon nanowires, the energy between the silicon nanowires decreased. And as we know that energy does not go inside the silicon nanowires themselves, the energy is getting transferred to the functionalization layer, which is something good for us because in the end, it is the functionalization layer that is actually detecting our target molecules, that is the lung cancer cells. Thus, if there is less energy between the silicon nanowires, it means that more energy is trapped inside the functionalization layer, which will help the functionalization layer perform better. So we see that with increase in functionalization layer coverage, the performance of the optical biosensor becomes better. Hence, silicon nanowire should be completely covered, and also overall, the effective refractive index is increased. The results show that nanowire waveguides have high sensitivity for early detection of lung cancer, and the rectangular bulk waveguide fails to detect any lung cancer biomolecules. Both the electric and magnetic field distribution inside the rectangular as well as nanowire waveguide suggest that mode present is positive. It was demonstrated that there is no change in Poynting vector profile of the rectangular bulk waveguide even after adding the functionalization layer. Therefore, it can be concluded that the rectangular bulk waveguide is not suitable for an optical biosensor. But the X-cut intensity pattern of the nanowire waveguide with functionalization layer has a completely different and non-overlapping pattern with nanowire waveguide without the functionalization layer. The increase and decrease in Poynting vector value at various places in the waveguide is due to changes in the refractive indices at the boundary of two materials. These multiple changes suggest us that functionalization layer of nanowire waveguide creates a change in the energy distribution of the waveguide and thus can be used for detection of biomolecules. Also, more functionalization layer coverage leads to better detection. These are the references we had used. Thank you all for being such a wonderful audience.